Global demand for energy is growing rapidly and will continue to increase with worldwide economic development and industrialization. The time is now for developing the scientific and technological foundations for promising energy sources that are safe, clean, and abundant.
Fusion would be an attractive energy source for the long term, as it is a source which has an abundant fuel which is sufficient for thousands of years of energy for all of humanity. It is also clean in that it does not produce large amounts of carbon waste. It doesn't produce high-level radioactive waste. It can't melt down, can't blow up. And generally, the geographical distribution of the fuel would be very stabilizing from a geopolitical perspective. ITER is an international partnership aimed at demonstrating the scientific and technological feasibility of fusion energy. It focuses on producing a burning plasma which is self-heated. The fusion reactions themselves keep the plasma hot. And this burning plasma is a very exciting and interesting scientific object that has not been observed here on Earth. As a large-scale international collaboration, ITER is also a new experience. We have united many nations of the world, more than half the world's population, in addressing a global problem.
ITER is an international collaboration of 7 partners, including the United States, People's Republic of China, European Union, India, Japan, Republic of Korea, and the Russian Federation. Member nations have worked together to develop the ITER design and are now engaging industry in their own countries in assuring manufacturability and fabricating prototype components.
Science is essential to achieving the ITER mission. From past experiments and theory, we know that fusion can produce energy. ITER is focused on producing a large amount of power. Matter of fact, enough power to keep the plasma hot. Achievement of that self-heating condition would be a monumental accomplishment. Not only would it produce energy, significant amounts of energy, but it would produce a scientific object which would be interesting because the plasma is now dominated by the dynamics of the fusion heating. This would be the first time it's been seen in a magnetically confined experiment. ITER uses very strong magnetic fields, 100,000 times the strength of the Earth, in order to contain the plasma's power so that it can stay hot. ITER as such is not just a physics experiment. It's also an engineering experiment. We are producing a plasma at reactor scale, and we're using many technologies which are relevant to a fusion reactor.
The construction of ITER in southern France is progressing rapidly. The first buildings are nearly completed, while the tokamak complex is being transformed from a giant pit to a seismically isolated building for the unique ITER machine. US ITER is a Department of Energy Office of Science project hosted by Oak Ridge National Laboratory with partners Princeton Plasma Physics Lab and Savannah River National Lab. As an ITER member, the United States receives full access to all scientific findings and new technologies, but will contribute less than 10% of ITER's construction cost. The U.S. is providing hardware for 10 different systems to ITER, including 2 kinds of magnet systems for confining and controlling the plasma inside the tokamak, tokamak cooling and power exhaust systems, plasma fueling, pumping, and disruption mitigation systems, ion and electron cyclotron transmission lines for plasma heating, multiple diagnostic systems to monitor plasma performance, and the steady-state electrical network. These hardware contributions will be built in the U.S. and shipped to the ITER site for assembly and research operation.
The U.S. is providing 2 magnet components. One's a central solenoid, and the other is a toroidal field conductor. Both of these are essential to plasma operation. The toroidal field conductor is going to be wound into the large toroidal field coils that provide the main stabilizing field for the plasma. The central solenoid modules will drive the plasma current and shape and position the plasma. ITER is very different from present-day tokamaks. In linear dimension, it's twice the size of the largest of the present-day tokamaks. This makes the plasma volume an order of magnitude larger than anything that we have today.
The tokamak cooling water system will surround the giant ITER device in order to exhaust heat generated during the operation of the facility. The cooling water system is very unique in that it will service huge plasma-facing blankets, plus diverters, and the vacuum vessel.
It does many functions. It bakes, it drains, it dries the water from the system, and it also has a function of controlling water chemistry. Interesting, we have pumps to move the water and heat exchangers to remove the heat and pressurizers to maintain the pressure, but we've also got 34 kilometers of piping that's arranged in a complex configuration to remove the heat from this unique experimental device.
The United States is making significant progress on its contributions to ITER. During 2012, the project will be transitioning from R&D and design activities to preparation for industrial production.
It's really critical for the central solenoid to get industry involved in the design phase. Industry is going to be responsible for building the components. We need to get them on board early to ensure the design can be manufactured and to identify ways to build components faster and cheaper.
By working closely with industry, US ITER is able to assure that components are designed in a way that is cost-effective and meets the necessary performance requirements. So far, US ITER contracts have been placed in 38 states plus the District of Columbia. To complete its contributions to ITER, the U.S. plans to award and manage an estimated $1 billion in future contracts. US ITER is moving forward. By 2013, U.S. components will start to be delivered to Europe. Additional hardware will be manufactured and delivered for first plasma operations in 2020 and later for full power operations. US ITER brings together science, engineering, research, and industry to contribute to one of the biggest challenges of our times: how to produce clean, abundant energy for generations to come. By producing, studying, and refining a reactor-scale burning plasma, ITER will help the future development of fusion energy. To learn more about US ITER, visit usiter.org.